Girls, Mr. Barr again. I thought I would just pop on to make another video just to hopefully explain our polyatomic ions a little bit differently. So we should have recapped this on Monday. But what we're looking at is polyatomic ions are just pretty much like groups of atoms that are always kind of transported together. So that's why they call them polyatomic. So poly, not like Polly wants a cracker, but that just means like pretty much more than one. Okay, and atomic just means atoms. So again, what this means is pretty much a polyatomic ion is kind of a group of atoms together, but they always seem to always go together in chemical reactions. So they're known as polyatomics because whenever we write them and whenever we talk about reactions, they always move together and they're always fixed. So things like sulfate groups, phosphate groups, things like that, which you probably have heard of before. But that's the reason why we give them those particular names, because they actually have particular chemical structures. And the unique thing about them is they all have a very fixed charge. So you can almost think about these as kind of like elements on the periodic table in terms of they're fixed. Whenever we talk about reactions when they're going against each other, they have particular charges. And when we start to balance out the actual chemicals, that's something we really need to think about. So these are some of the more basic ones we talk about, things like your phosphate groups, all right? Sulfates, carbonates, nitrates. Ammonium is actually probably one of the only positively charged ions, particularly the polyatomic ones that we generally deal with in junior school. And the other one is hydroxide. And again, you probably have heard of hydroxides before as well, but potentially thinking about it, writing it chemically, it's a little bit different. So when we're naming these things, it is pretty much the same process as when you're naming a normal kind of a chemical here. Really, these are generally ionic substances. So therefore, we don't need to put like diphosphates or anything like that when it comes to it. Same with the metals as well. So generally, when we're looking at all the chemicals now, we're going to be using similar naming to ionic. All right, and that's because the polyatomic groups have got their own names, so we don't have to do anything else with it. So particularly when you start to see these in equations, you can actually start to go, well, these are actually polyatomic. So these are actually I probably need to think a little bit deeper on these. So these are probably the 5 you would need to know. I wouldn't worry too much about ammonium. If you do remember it, that's fine, but definitely I would say your carbonates would be something you need to remember, your sulfates, nitrates, and definitely hydroxides. Phosphates we don't normally do a whole lot with, but if you can remember that too, that would be great. But as you can see here, it gives you what the structure is. So in case a phosphate group is a PO4 group, so P meaning phosphorus, oxygen, and it's got a -3 charge. So it's almost just like, you know, when you go to the when we go to a periodic table. Oh, let's see if I can bring that up. Did I close it? Looks like I did. I'll reopen it just to show ya. So again, just like when we go to a periodic table, we see its valency. Its valency is almost like another word. So whenever I say the word charge, I'm kind of talking about its valency. All right. You go away, so I don't have to do that. So again, like we talk about elements having certain valencies or certain charges. So like everything in group 1 is going to have a +1 charge. Everything in group 2 is going to have a +2 charge. Group 13 is going to have a +3. But instead of that, these polyatomic ions have their own charges. So phosphates are always going to be -3. Carbonates are always -2. Sulfates are always -2. Nitrates are always -1. And hydroxides are always -1 as well. And ammoniums are +1, which means they give away an electron rather than gain it. Okay, but naming them just as easy. So what we need to do is I've got an element, I've got a chemical here, and I can kind of know that it's a hydroxide group by just looking at it. So I've got two things. I've got the metal plus the other elements. So I already know Li. Again, if I want to go back to my periodic table, it's lithium. All right, pretty easy. So I'm going to write that down. So lithium, easy peasy. I'm going to go back to my table up here and have a look for if there's an OH group. Now I'm not going to worry about charges when naming, remember, and I can clearly see that it's hydroxide. So I'm going to write that down. Ooh, very pretty, Cameron. So again, now we just plug those together. We don't have to do anything in terms of changing its name here. So we're not going to call it hydroxum or anything like that. This IDE stays because these are fixed. They're always polyatomic ions, so we don't need to do anything with its naming. So what I'm going to do is I'm going to go to naming the compound and just put that together. Lithium hydroxide. And that is now that is now the name of this chemical, which contains a polyatomic ion. Easy as that. Now, what we're going to do is we're going to be able to go write a formula as well from that, and potentially, hopefully, you're able to get the stuff on Monday. We went through it pretty well, I hope. But we'll be able to. It's pretty much a similar process to the crossing over method that we used before. So again, what I'm going to do is I'm after calcium carbonate. And what I need to do is I need to write element 1. So this is going to be calcium. All right, calcium actually is a 2+ charge. All right, so again, going back to our periodic table, calcium's in the second group. That's how I remember it. I almost remember what group it's in, and that just gives me the charge. Again, I've probably had a lot more chemistry experience than you. I've probably, whatever. Who knows how long I've been doing chemistry for? Probably way too long, probably 12 years now. So I would have started, 16? Yeah. That's what happens when you get old. But anyway. So that's going to be a 2+ charge. And again, we don't really care about its charge, to be fair, when we're doing this stuff. So it doesn't really matter. So we're going to get calcium with a 2 charge. Now our polyatomic ion is carbonate. So I go back up to my table and I see that carbonate is actually here. The carbonate is a CO3 group, but its charge is also -2. All right, so I'm going to write that. Carbonate, and it's going to have a 2 charge. Now remember, we can cross these over. But as we remember with our sodium magnesium oxide example, if both sides have 2, now, this is where it gets a little bit tricky because actually, when you're talking about polyatomic ions, you actually have to put brackets around when there's any more than one. And I'll show you an example where we actually have to do that. So I'll show you that I'll actually do calcium nitrate with you to show that. But what we're going to do is we know that's not the case. So we always know if there's 2 on this side and 2 on this side, which it would have been with the carbonate group, we kind of just cancel those out. We don't really care about them, to be fair. So what I do is I will just write calcium carbonate, and now that is ticked off because really this is a -2 and this is a +2, and really if you want to do the maths, you just add those up and that should equal 0, which actually goes to show you that this chemical is actually pretty neutral. It's actually a neutral substance, but we don't need to know that for our level of knowledge. But I'll show you what to do in case you've got a bigger chemical. So for example, I'm going to write something called calcium nitrate. All right. So calcium, I already know is going to be Ca, and it's going to be a 2+ charge. But nitrate, if we go up to our table, it's actually what we call an NO3 group. All right, but as you can see with its charge, it's only got a -1 charge. So that's going to throw our little maths off a little bit. So calcium plus nitrate. So what we need to do is we need to cross these over, but there's one important thing we need to do with the nitrate group. Okay, so really what we need to do is we need to cross it over. So technically Ca has got a 1 here, but we don't write that. Remember that. But then we need to technically write 2 nitrate groups. And the way we do that is we don't just put a 2 here, because otherwise that kind of looks to me like there's actually 32 oxygens, which we know is not the case. And again, we don't write this as well because it's not a true reflection of the actual polyatomic ions. The polyatomic ion groups are actually different to each other. So for example, what we're actually going to do is we're going to put the NO3 group here. We're going to put it into a pair of brackets, and then we're going to put a 2 over here. Okay, because if we actually drew this molecule, it'll be a calcium. All right, and when we do the bonds to it, it would actually be like a nitrogen group, which would have an oxygen, oxygen, oxygen. Now this isn't super structurally correct, but this is actually what it looks like. So again, like if we spoke about what were the different chemicals in here, we'd have an NO3 group, an NO3 group, and a calcium group. So that's why we almost have to do it in this way, because these groups can break off and do their own reacting. Okay, so that's quite important. So whenever you do something like this, but the opposite's true. If I was going to do something like sodium, let's go down here. If I was going to do something like sodium, so let's just say sodium, which has got a plus charge, and I'm going to do carbonate, which is CO3. As you can see, it's a -2 and +1. When you cross those over, you just write NO2CO3. So again, we've still got our same things. Technically, this is telling us that that's a 1 there, and we don't need to draw that. Okay? So again, a bit of extra stuff. Hopefully, you'll be able to have a play around with that too. So therefore, we've got calcium carbonate is our reaction. We've done that crossover event. So that's really, really good. Now, transition metals, as I told you before, the reason why we can't give a valency for the transition metals is because they don't follow the same structure as our group 1, 2, 13, 14, 15, 16, 17, and 18 in terms of the groups. The transition metals are weird and they do their own things, okay? So what that means is consistently, these valencies can change. So what that means is the amount of electrons that they can do reacting actually changes. It doesn't change in the reaction, but particularly when it comes to, you might have some metals. So for example, manganese might be a 2+ in some cases, or a 1+, or a 3+, or a 4+. Same thing with particularly copper. Copper can be 2+, 3+, or 4+. So we don't actually know what they look like until we look at the actual formula that they give us. Okay, so what I look at here is there's an amazing thing called is the actual bracket there tells you what its valency is. So as you can see, I've got a mercury 1 iodide. Okay, so in that brackets is a Roman numerals, and whatever are numerals in there actually tells you the charge of the metal. So that is pretty much one thing. Okay, so mercury iodide, I'll get rid of that. Oh, so mercury iodide. All right, so that's almost one thing, and then you've got iodine being the other. So it's actually kind of easy to do. So again, as I said, it gives you what charge you got. So this is going to be +1. So when I'm actually writing the chemical formula from a name, I write down what mercury is. Now, mercury, you might have to have a bit of a hunt around for these elements, but mercury is right here. Okay, it's one of those famous ones. This is probably one of the ones you do need to know, just because, hey, it's got a weird name, so it's mercury. It's one of the ones that are liquid. It's only like pretty much 1 and maybe bromine at certain conditions can be liquid. Was it bromine or iodine? I think it was iodine, sorry. So mercury is one of those things you kind of remember that. And it's also got Hg as well, so it doesn't link towards its name. So that also is another reason why it should stick in your head. But as you can see, it's in the transition metals, which means it can vary in its charge. Now, there is one exception. So silver is always +1. But again, I won't delve into that too much further as well. So what I'm going to do is I'm going to write down its chemical, so Hg, and it's got a +1 charge. All right, when I go to element 2, it's iodine. Iodine is just I, and it's got a -1 charge. Now, if I do the crossing over, all right, you know that's just going to be Hgi. Easy as that, okay? Now, if, let's say it was mercury 2 iodide, all right, same process would apply. This 2 here gives me the charge, so it's going to be Hg, 2+, and then it's going to be iodine, which is -1. All right, cross those over. It's going to be why did I do Ag? It's not silver, guys. So that means that's going to be Hgi2. All right, and that's because really this mercury 2 means that this has got a 2+ charge, and the iodine here's got a -1 charge, but you need 2 of them because technically Hg will give 1 electron and it'll also give another electron to the iodide, making it happy. All right, so that's our answer for that one. So hopefully you better give that a go. Now, writing the formula again is just a little bit easier. It's kind of the same, but I kind of invented this calculation to do it. I mean, I'm probably not the only one. I can't imagine I'm the one, but I know some of you are quite mathematically minded, so this might help you out in terms of doing that. So what we need to do is, I've been given this, and this tells me that I have some iron atoms and I have an iodide atom, or iodine atoms, okay? And I've got 3 of them. Now, in my head that works straight away and tells me the answer, but remember before that transition metals can have, as I said, different numbers of valence electrons, so their charges can be different. So therefore, I need to know what type of ion this is, whether it's iron 1, iron 2, iron 3, iron 4, iron 5, whatever. So I'm going to do the same process before. So Fe is equal to iron. So I already know that's the case. And remember, it's the metal, so its name doesn't change. I then have an iodine. Sorry, my laptop just went blah. So now I have an iodine. I know I'm already going to shortcut them and write it as an iodide. But now I need to find out actually. I need to find out question mark, what is my Roman numerals going to be? So what I need to do is I need to find out for X. So I'm going to put X as my unknown, and that's going to be here. That's going to be the Roman numerals is going to be X. Okay. Now, if I look at the front here, I've only got 1 iron, so I don't have to do anything with X. If you have 2, you'll have to put a 2 in front, and I'll show you an example of that. So this is X, and what you're going to do is you are going to do the subscript of the element, and the element is actually going to be this one here, so element 2. So I probably should change that and write element 2. So subscript number of element 2, because that's one we're attached to. So in this case here, it's going to be 3. All right. Number of element 2. Let me just type that in there so you actually understand. So subscript of element 2 plus the valency of the element. So in this case here, if I look over at Fe, it's got a 3. So what I'm going to do is I'm going to X equals to 3. And I'm going to times it by the actual valency of the element. And iodine, as we know, is -1. Now, we don't have to worry about negatives here because the only reason why is all of our chemicals that are really attached to metals are always going to be negative because metals want to give away their electrons. So what I'm just going to do is 3 times 1. Okay, and therefore, if I do the calculations, that means that X is going to be equal to 3. So that means I now need to write it as iron 3 iodide. All right, so if I look over here, chemical name, I'm going to write iron 3 iodide. Now, there's a way you could probably do it a shorthand way, and again, it's just by looking at it. So if I looked at this chemical here, which is FeI3, I could really just go, okay, well, the iodine has got a -1 charge, and there's 3 of them, so that means it's going to be 3. And because this is neutral, that means I need a 3 plus here. So I really don't mind how you do it, as long as you do it in a consistent way. And I know the maths can help some people, but that's the way my brain would do it. So again, I would know that since iodine is a -1, I have to times that by 3 because there's 3 of them. So therefore, it's a 3 negative. This molecule needs to be 0. So therefore, I need to have a 3 plus here to neutralize that. So it's up to you how you do it. That's a shorthand, but pretty much I've just shown you the maths here of the exact same way to do it. Okay. So give that a go if you can. Run the formula. So you always just need to, our main culprit is going to be this one here. Okay, trying to find that Roman numerals. All right. So that's going to make things a tad trickier. I'm trying to think if there's a case where it can get trickier. Nope. So pretty much you'd always end up just writing what's there. Now, at the end, there's another one which is going to be a little bit trickier. But this is where you actually need to write the chemical formula for this. Oh, sorry, you need to write, need to write the name for it. I think going from chemical, can I give you another one? Maybe I'll do that one too. We actually go from chemical name to chemical formula. But again, did I do that? Anyway, I'll give that to you and it shouldn't be too hard to do. I'll show you an example. So I'll do one down here, which is like, let's do lead to nitrate. We'll do that at the end, okay? But really, it's the same kind of process that we've been doing above, but it's just that we need to know that our polyatomic ions have just got fixed ratios. Just almost pretend it's an element and that you know the charge of it, okay? So I already know that I've got a copper and a carbonate. So what I'm going to do is I'm going to write copper. Now I'm going to write the actual name there. So copper. All right. Now I'm going to write my polyatomic ion name with its charge. So again, I can do that too just because I know, and that's a carbonate ion. It's CO3, and it's got a -2 charge. We don't know the charge here of this copper unless we do a bit of maths. Now, I actually know off the top of my head what it is, but I'll show you that too. So copper, we need to know what the charge is going to be here. I could do my subscript thing again, so X. But remember, when we go to our copper here, we need to realize that we've actually got 2 of them. So that means it's actually a 2X we're looking for. All right, 2X is equal to the subscript of the polyatomic ion. Now, as I said before, because this is not in brackets, we're just going to assume it's 1. So therefore, it's a 1 times the valency, and the valency of carbonate is always -2. So that means it's 2X is equal to 2. You've got to split those in half. So X is equal to 1. So when we're writing the name, I can now say that this copper here has a 1 plus charge. So that means I'm going to write copper 1 carbonate. All right. So when I'm doing this, I'm going to go copper 1 carbonate. All right. Oh, come on, Bayer. Come on, Bayer. I'm just going to write it below it so there's no room. So copper 1, actually, carbonate. All right. And I've been able to calculate that. And again, if you really want to do a shortcut, so Cu2CO3, you would just write that this is a -2 charge. There's only 1 of them because remember, we could almost pretend that this is in brackets. So 2 times 1 will give you 2. So that means over here, this has to equal -2. And because there's a 2 there, it means, that's +2. So that means those two equal up to 0, which means it's neutral. And again, you could do the shortcut where, well, you've actually got 2 of these atoms that give it a whole 2 plus charge. That means overall it has to be a +1 charge. All right, so you can do my shorthand or doing this maths here. It ends up finding out the same way. And potentially, until you get more comfortable with the calculations, that might help out as well. Just going from lead nitrate, this one's a little bit trickier as well. But all I need to do is I just need to write down, again, its charge. So I've got PB. The 2 here tells me that's +2. Nitrate, NO3, it's a -1 charge. Again, going back to that table, we do our crossover event. Now we have PB. I put in brackets my nitrate because I already know there's going to be more than 2. All right. So therefore, that is now lead nitrate. All right. If I was going to do lead hydroxide, it would be the same thing. But if I did something like, I don't know, lead phosphate, and this is going to be one of the hard ones. I think I gave you a question on this. But again, it's just going back to the group. So again, PO3, -4. So it's actually got a, no. Let's write that around the other way around. It's 4, -3. Lead, we know is PB. It's got a 2+. Do our crossover event. So that means this is going to be PB. And it's going to have 3 because that number goes to there. And then we're going to have our phosphate group. And what we're going to do is we're going to have 2 because that number now goes to this side. All right, which means we've got PB, lead, phosphate. Well, lead 2 phosphate. If it was lead 1 phosphate, we would need, again, if it was just lead 1 phosphate, so let's see, PB 1 phosphate -3 crossover, it's just going to be PB3PO4. So again, as you can see, every single time we do this, this phosphate group kind of goes as its own group. Okay, hopefully that makes some sort of sense. I know I moved through it pretty quickly, but slow down. But again, it's just applying the same namings we were doing before. I'll give you a whole day to apply those. But this is really extension stuff. So if you see yourself just going like, all right, this is just too tricky, particularly this transition metal stuff is very much a bit beyond where you need to be. However, I believe in every single one of you that you can probably do this. I'd say everyone can. But at worst, you really want to push yourself. This first part here of the activity that's in the Google Sheets that I've given you, give it a really good go. Okay? I want you to push yourself and try really hard because you all can be amazing chemists. I believe in you. Hey, have a good day. Take it easy.